Okay, so let's see. Okay, well, today we're going to talk about robot chickens and how a Netduino secures and feeds our backyard flock. And as I started working on this presentation, I thought, you know, if I'm going to be totally honest, I should have called it how a Netduino is going to secure and feed our backyard flock, because obviously all of the components are here with me now today, which is great. It lets me show it off in real time. But then that got me thinking about, well, what else could I have titled this presentation? And one that I came up with was how to spend a lot of money and a lot of time to get out of a chore that takes 5 minutes a day. And that's the reality of it. I mean, this is what we technology people do, right? We see some problem and we want to find a technical solution for it. So we invest our time, and the reality is that what this is going to achieve is not anything that's earth-shattering. Oh, it is. But, you know. So then from there I thought, well, here's how to hijack your wife's Amazon Prime account and make them think she's a total geek. Everything that's on this table here is available through Amazon. These are very standard components. There's nothing particularly magical about what I've done here. And Jamie, is Jamie here? Jamie was insistent that I actually like cage up one of our chickens and bring it, but I couldn't do that. So I brought this guy. So she'll sit here with us today. But so we are talking about chickens. So these are my 4 chickens that live in our backyard. In a stroke of grand cosmic irony, we used to have 5 chickens, but while I was preparing all of this, we were out late one night and the sun went down and we weren't home in time to lock him up, and a predator got his jaws on one of them. So these are the 4 we have now, named by my 7 and 5-year-old, Dolly, Brownie, Izzy, and Vader on the end. That was mine, and a black chicken. Regardless of gender, it has to be Vader. So this is the coop that they live in. This is in my backyard. This was built off of using plans off the internet. And you know you're kind of in deep with animals when the free chickens that are given to you by your neighbor, the first thing you have to do is go spend $300 on lumber to build a house for these free chickens to live in. But this is where they live, and it's a 4x4 square. And like I said, we've got 4 now, but we've had as many as 8 chickens living in this coop. So if you don't know much about chickens, they basically do a few simple things. They eat food, whatever you throw at them. They scratch up the ground and find bugs. They poop pretty much on everything. Occasionally they'll squawk and make some noise. The whole reason we do this is because they lay eggs, and then they sleep. And the sleep part is a lot of what we'll sort of talk about today, because chickens are intuitive, natural photosensors. Chickens will rise up at the dawn, ready to go, ready to start their day, and as soon as they see that the sun is going down, they will climb into that coop and roost together and be ready for the night. So they have this very cyclical sort of experience, and so as the days change, we just went through daylight savings time. You always have to sort of be aware of when the sun goes down, because the other reality about chickens is that they are subject to many predators. So in my backyard, I've chased away foxes. I've seen a weasel who, I'm here to confess, found himself at the business end of a firearm. We've seen plenty of raccoons. We've seen possums. These are all threats to these animals. And so the need to secure them and have them be in a safe environment is sort of the reality, the responsibility of the chicken owner. But again, it's inconvenient. In my house, every morning over breakfast, we have this little debate about who is going to go let the chickens out. Is it the 7-year-old's day or the 5-year-old's day? Or is Daddy just going to go do it because he's tired of the bickering? And then at night, every night, they have to be put away. So when the sun goes down at 5:30 or 6 o'clock, as it does right now, if you're out for dinner or out doing some activity, the chickens have to be put away still the same. And so that's really what motivated me to find a solution for this, and it really had two basic parts: automating the door, which is this unit here, and then automating the feed, which is that box there. And the general kind of code aspect of this is very straightforward, right? If it's light outside, then open the door, let them out, and throw some feed out. Or if it's dark outside, then close the door and lock them in. So it's a very simple problem to solve, but as we start to unpack this, there's a fair amount of electronics that goes into it. There's a fair amount of kind of unique engineering challenges that I found. And so that's kind of where I want to go from here, is to talk about what went into this, and maybe by next year I can report back how successful this whole process really was once we get it installed into the coop. So, components. I mentioned earlier this is all available on Amazon. There's basically the heart and soul of this thing is the Netduino. Again, I chose to go with the Netduino Plus 2, which has an Ethernet connection, under the hope that someday this whole system would be able to be monitored via a smartphone or through an internet connection, to the point where we could control these, or at least kind of check the state. Did the door actually open up like we hoped it would, or are the chickens trapped inside the coop and it's lunchtime? And so this uses the .NET Micro framework is the SDK from Microsoft, and then there's also a Netduino SDK that we leverage. And so again, this is a $60 product. There are other versions of the Netduino, particularly that don't have Ethernet, that are a little bit less expensive. What we really want are kind of those blue pins, and that's how we're interacting with all of the other components. So to drive the door, we have a DC motor. This was about a $14 purchase. It runs on 12 volts, and it runs at 25 RPMs, which is suitable enough to lift up this door. The trick about this, and the reason we need another component called a motor controller, is because we want to be able to determine what direction the motor turns. So I need to be able to say, go clockwise and rise the door up, or go counterclockwise and lower the door down. And so the motor controller allows me, gives me that interface between the motor itself. My first pass at this, I was trying to be thrifty, and I was trying to recycle an old cordless screwdriver I found in the garage, which had plenty of torque. It certainly had the ability to lift the door up, but found that the draw of electricity when that motor would turn exceeded what the capacity of some of these components was. And so that was sort of a learning experience of suddenly now it's not just, well, here's a motor, it turns, it takes power. There's the second level of consideration of things like amperage, and you don't want to burn your board up by drawing too much electricity through it, and those sorts of things. So I had tried that several ways to try to get that to work, but in the end chose to purchase a motor that was pretty straightforward. The next component for the feeder, which is sort of hard to see, it's underneath the box there, is a servo motor. And so this is a little bit different in the sense that it has a range, right? There's sort of a range of where it will turn. And so that's how I'm underneath here, what you don't see is that there's a sort of a trap door that will slide to allow feed to drop through there. So the servo is pulling that back and forth. Then I have two LEDs. So this is my control box. This will be mounted on the side of the coop. And so I have a red LED and a green LED. So this is borrowing from my alarm panel in my house, right? Is it armed or disarmed? So is the door open or is the door closed? And the intention here was, if I can go out my back door and look across the yard, I just need a visual indicator of what state the thing is in, just as a spot check, basically. And then the final piece is what's called a photoresistor. And so this is essentially the component that's going to detect the amount of light in that environment. And so, so this is really what's going to set the timing of it. One thing that's a little unique about the Netduino board is it doesn't have a real-time clock in it. So you power the thing on, and it doesn't know that today is November the 8th. It thinks it's the day it was created, which is somewhere in probably 2011, right? So rather than trying to control this whole thing based on what time of day it is, we use the photo sensor to detect the conditions and then act accordingly. And so we'll see how that gets wired up in a little bit. The development environment for this, again, is all Visual Studio. Let me switch over and I'll show the Visual Studio side of things. One thing that happens when you install the micro framework and then the Netduino add-on is you get this set of project templates. And so you can see here that each of these kind of matches to the different particular version of the hardware. And that template stamps out kind of knowing, what the capabilities of that particular model are. And so, but then everything from here is sort of normal Visual Studio development. The one caveat to that is because you're using what's called the micro framework, they have reduced down some of the capabilities that you would find in the larger .NET framework. So the simple example is something that we take very much for granted, of like reading a configuration value. The system.configuration namespace is not in the micro framework. So that task has to be handled a different way. And that's a way how they've reduced that down so that it can be deployed efficiently onto this limited capacity piece of hardware. But once you get your project set up, then everything else in Visual Studio is largely the same. And so what will happen is that once you connect via USB cable to the device, then in your project properties, we'll have this tab for the micro framework. And when you plug in your device, it will show up here in the devices list. And this is what handles when you actually want to debug your code. You essentially deploy it to the device over the USB, and you can run it in real time just like any other Visual Studio debugging. And then once it's deployed on there, whatever the last version you deployed is the one that will run when you would power that device up. So the USB connection becomes the deployment process for your code as well. So the next, so let's kind of unpack the different parts of this. So the photoresistor. So the photoresistor, one of the things that I will sort of narrate through here is, oh, that was it. Is the wiring diagram for this thing. So one of the tools that I found that will take a moment to load up here, I think. Here we go. So this is a tool called fritzing, and it is a very cool tool for sort of building these wiring diagrams. And so again, if you've ever taken a electronics course or a physics class, you may be familiar with the item at the top, which is called a breadboard. This is essentially kind of a way to connect things together. This tool does not have explicitly the Netduino version, but it has several of the Arduino, which is sort of the open source variant. And so this one has the same pinout as the Netduino that we have here. But then I've got the servers, or the servo and the motors and the LEDs and all these things. So I can kind of narrate through this. And essentially how all of these components work is when you plug something in and there's an electrical current to it, then it will flow through these lines to complete a circuit. And based on the amount of electricity flowing through that circuit at any given time, then that is largely how you're interacting with these components. So for example, if I want to take a reading from the photoresistor, I'm measuring the properties of the current that is flowing through that loop all the way through. If I want to send a command or light up an LED, in code, we'll see I'm signing a true value, but what that is really doing is it's opening up a gate to say, let current pass through this circuit and complete the circuit. So as we kind of look at the photoresistor side of things, the first thing we get, we can kind of follow the line here. So this first line coming out is taking electricity from the Netduino board up onto the breadboard. It's then going to flow up through this resistor and then come back down this line here, and the blue wire here is going to connect to our analog input-output port. So this is where we're actually going to take the reading for this circuit, and then it passes through that, and then this red line, you see it kind of comes across to the photoresistor itself and back through to the ground, and then that returns to the board. So it's a complete circuit all the way through. And a photoresistor is a little bit of a unique application because you have to use what's called a voltage divider. Now, I'm not here to lecture you on how electricity works and Ohm's law and these sorts of things, but suffice it to say that when that current goes through the circuit, there are certain properties to it that are proportional and consistent. And so in this case, where I have a circuit where I have one value that's fixed and known, that's the resistor on the top, and I have another value that's variable, which is the reading off of the sensor. By taking a measurement in between those two in the circuit allows me to detect the change in voltage that happens on that circuit at that point, because the proportionality is going to be consistent. Now this took me a little while to figure out, and one of the things that happens is when you read in on an analog, right? Analog means there's a whole range of values. It's not just a true or a false. There's a whole range of values. You then have to sort of know how to interpret whatever value you're getting back out. So the first thing I had to do with Visual Studio was I actually wrote a little program just to be able to calibrate the photocell. And so what this does is essentially it just creates a loop, right? So this is just going to loop on through, and that sleep interval you see there is probably 1 second or 2 seconds. But each time it goes through the loop, it's going to read a value off that sensor and output it to the console. And so this was a way that when I ran this, I could say, okay, here's what I consider a light condition. What are the numbers that this is spitting out? Now when I put a piece of tape over that photocell or shut the lights off in the room, let's see how the numbers change. Because ultimately, for my application, I have to be able to have some thresholds, right? To determine, to tell the rest of the program, is it a light condition or a dark condition or somewhere in between. And so by calibrating it, in this case, it goes from a 0 to a 1 and all numbers in between. I sort of calibrated it to say, okay, if it's greater than 0.75, that represents a dark condition, so we'll set that value. If it's sort of in between, this is sort of the twilight stage, right? It's getting dark, but not fully dark yet. What's that range? And then finally, anything less than a 0.49 in my case was considered light. Now, this was my set of numbers based on the particular photocell I'm using. And there's a rating that's on that photocell for its own sort of range of resistance. So that's why I kind of just wrote this program to figure it out on my own, to say, okay, well, let's just try to create some conditions and take the values off of it. So the next part of our unit then are the LEDs. And so the LEDs are basically, again, we can kind of follow the sequence here. So I have pins 3 and 4 corresponding to the LEDs. And again, if we sort of follow the path here, we'll come out of the Arduino or the Netduino, we'll go up, we'll go through a resistor to kind of measure down the voltage a little bit, then we'll come out through the light and back to ground. And so that's a complete circuit. And again, when I want to turn that LED on, essentially all I'm doing is saying, put a true value on this port. And basically that allows the flow of electricity to go through that. And so that makes it very simple. There are other applications where you might have like a dimmable LED, where it's a little bit of a different experience, a different process to vary the range of how much electricity is. But since I was just turning things on and turning things off, it was enough to just turn it true or turn it false. For the, go ahead, question.
You probably can also jam an LED with a pulse width modulation technique where you just put
Correct.
it in a neutral and turn it on for 25 or 40 or 50, 60 or 75%.
Correct. Yeah. And so the term he used there, pulse width modulation, we do actually use that with the servo for how we determine or communicate to the servo what position we want to be in. I'll talk about that in a moment. For the motor on the door, again, the challenge here is being able to tell it go one direction or go the other direction. So that occupies really 3 pins. So my first pin is an enable disable, just turn the motor on or turn it off. The second pin then is a true false value representing one direction, and the third pin is a true false value representing the other direction. So we'll see in the code, when I want to open the door, I set one pin to true, one pin to false, and then enable it, and that tells this little chip, the motor controller, to change the polarity of the electricity flowing to the motor. And then the opposite of that is, the reverse of that is what tells it to rotate the motor the other direction. And so the motor controller chip that I have will actually let you drive 2 motors. So you would use 6 pins on your board, but then you could have 2 independent motors, each being able to rotate independently in each direction for one another. Then finally, the servo for the dispenser, again, is a little bit of a different case, where I have a separate power supply that's feeding in power to the servo here, and then the signaling wire that comes across uses, as the gentleman mentioned in the back, what's called pulse wave modulation. So again, this is not a physics class, but when you send an electrical current over it, there's a frequency to it. It's sort of like a wave. And the height of that wave determines how sort of strong the current is. And then the length of that wave can carry some properties for it. And so the way that servos work is they say, okay, if I'm going to put myself in the 0 degrees position, right, then I'm going to orient that based on a, say, 1 millisecond pulse of electricity at a certain current. And so we have to send that pulse for that measured amount of time. And then if I want to swing it to 180 degrees, then instead of a 1 millisecond pulse, it might be a 5 millisecond pulse to represent that position. And then you sort of get all the increments in between. So the good news of this is that the SDK provided by Secret Labs, which is sort of the manufacturer, if you will, of the Netduino, they have libraries already sort of formed to handle that calculation, right? So I have the ability to say, well, go to 0 degrees or go to 180 degrees, and that's all my interaction is. But it's been abstracted out so that it figures out the pulse mechanism to actually send over the wire. When you buy a servo, it should come, this one came from Radio Shack, but it should come with a little table to sort of illustrate what those measures are for each position on the servo. And so using these values and then kind of calibrating it in code, you find what that range is that you need to call out. So that was, again, a lot of trial and error, a lot of experimenting to try to get these things to behave the way that I want them to. So let's see how the actual kind of main code is formed, and then we'll plug this thing in and see if it does everything we want it to. So one thing I found almost immediately when you're dealing with the Netduino, again, as kind of an embedded system, is everything runs in one main program, and largely everything needs to be declared as static, right? So if you're going to have something available to the whole program, it has to be declared as static so that it can see it. So I've kind of listed here some constant values for my thresholds and my intervals. So the overall timer interval is how frequently am I kind of running through my loop. I have a door open and door close interval, so I chose when this motor starts, I said, okay, it takes about 27 seconds for it to rise the door all the way up. So run it for 27 seconds and then stop. It's a little faster going down, so run it for 23 seconds and go down. And we'll see that later on. This is where I'm sort of declaring and associating the pins on the board with a port that I can now interact with in code. So you see here the digital port 0, 1, and 2 are for the motor. I then have an analog port, and all these sort of constant values or these enumerations are provided by the framework, the Netduino SDK framework. So it's very easy to kind of navigate this. I then have some logging. I have some state variables to sort of say what condition is the door in. Here's the class I mentioned about sort of an abstracted class for the servo itself. So I just declare it as a servo and initialize it to be associated with the pin that I want to drive it from. I have another interval for the feed dispenser. So again, open it. This was another sort of manual calibration, right? If I open the door, how much food falls out per second before I close that door? How long do I want to keep this open to dispense an adequate enough amount of food for the chickens? So that was an interval I have there. And then finally, the open and closed LED pins are defined. The Netduino itself has an onboard button, and I use this button as a way to kind of manually override the state of the system. And so I'll use that here, but I declare that so I can take a reading on whether that button is being pushed or not. So my main loop then, I do a little bit of initialization, but here's my sort of main while loop. And the first thing I do then is take a reading off the photo cell, and that's going to set a value for kind of the condition. I then read the button state so that I can, again, have a manual override to it. And then I come down here into sort of, looking at the conditions. If it's dark out but the door is already closed, I don't want to tell it to try to close it again, right? So I have to evaluate that state. And then if it is dark enough, go ahead and call out to close the door. When I go into the details of this, again, what I'm doing is writing these true and false values out to the pins to say, okay, these first 3 lines essentially start the motor going in one direction. I then pause and let it run for that interval. And then I call a method to stop the door, which essentially sets all those pins to false. And that will stop the motor from turning. And then similarly, when I open the door, I go to, I do a similar thing, right? But I change the direction that the motor turns. I run it for that interval, and then change the values on the LEDs to show the state, and go from there. So again, not terribly sophisticated code. It's more a challenge of just really figuring out the particular interaction with the hardware, how to call the pins, how to make sure that things are organized well. The last item then is the code for the feed dispenser, and again, this was because of the abstraction that was provided by this servo class. I can just say set it to 180 degrees, which will open it, and then pause for that period of time, and then turn it back to 0 degrees, which will close the door back up. And then there's a couple other utility methods I did, again, just for logging and recording some status out to so I can watch this as it goes. So, moment of truth. Here we go. So it's in a closed condition. I mentioned earlier I'm kind of using timing to rise and lower this door. Another approach that I may end up going to would be to actually put a switch at the top and at the bottom to be able to more closely measure what state the physical door is in. And so again, I would need to use 2 more pins to read those values, but that would allow me to be a little more precise about the state of the door. So when this thing starts up, it's going to assume it's in a closed state. The photo sensor is on the side of my box here. And so let's go ahead and plug this guy in, see what happens.
So, I mean, if it was up and your board reset, it's gonna say it's closed, and it's gonna try to.
And it's going to try to open it again.
And it's gonna probably burn out the motor then, right?
It will. This is another little engineering feat, right? How do we get these to stick? Put this time out. It'll be the longest 27 seconds of my life here. Okay, so yeah, engineering challenge number one, right? How do I get this cord to stick to the axle consistently? I got a piece of tape in there, so we'll see if that gets there. So I'm going to push the button here. So that should, as it goes through that cycle, it should say, actually that'll do it backwards because I think the door is open. So yeah, this is part of the argument for having actual switches, because then you could poll it to see what's the actual condition that it's in. Let me get this thing going. There we go. So I use these little pulleys. These are actually, I found, these are like, would be used for like a sliding screen door in your house. So I had used this to give it a little bit of mechanical advantage, just even though there's a lot more turning that's going on, the lift is a little bit, I didn't want to have too much downward pull on the motor. This is a fairly strong axle, but I didn't want to put too much downward pressure on it and kind of bend that. So, what else did I miss here? I missed a plug. Because our dispenser didn't go. Let's try it. The risk of moving things around as things get unplugged. So let me wire this back up.
You are connected to something important.
Yeah, I'm recording this, so this is my microphone. So let's get this in here. So, let's see if that's it. So I'm going to push the button, which should put it into a closed state. Again, it's a little bit of a pause. And so while I'm debugging this, I have that interval set at about 10 seconds, because I don't want to sit around forever. I think when I put it actually out in the backyard, I'll do a poll on about probably 10 minutes to take a reading for the light. And that will, kind of elongate that whole process. Because the concern, too, is that if the, for some reason, even if the chickens don't go in right away, you don't want to lock them out. So this will go through the polling again, and we should see it open up in a moment. Okay. And there's feed for the chickens. Brilliant. There we go. Excellent. So, that's right, yeah. Not anticipated.
You done?
Not quite. I just spilled popcorn all over the floor.
Does this board have interrupt pins or
Did you bring a chicken?
something like that?
It's right here, Jamie. I brought it for you. Yeah. I'm sorry, what was the question?
Does this board has an interrupt pins or input, something like that, like that will like break a process or something like that?
Oh, to like interfere with it?
Yeah, just like pin where it receives an input or something like that. It will like
Yeah,
you can read it without looping.
Right. Yeah. So, so you could get it to behave that way. Again, I used the button as a way to interact with it while it was running. If you wanted to have like an actual switch, turn the whole thing on, turn the whole thing off, you could do it that way.
I'm not sure, like,
Interrupt driven? Yeah, it does.
interrupt?
Interrupt driven, yeah, which you,
Yeah.
what would it be?
Yeah.
Yeah. You can interrupt driven software.
For the board itself.
It also supports threading, so you can create a thread that's monitoring that thing. So you can
Yeah.
do it that way.
Okay, okay. This is an answer. So you don't need to have a loop to react to something. You can
It's
just
just-
react
it's
on
easier.
an input of the pin.
Yeah.
Right, it's easier with the loop because you don't deal with thread blocks and all that stuff.
Okay, let me get this back out here. There we go. So, so there are a few things. Obviously, securing my feed dispenser is one. So there are some things that I've still have in mind for this. So this is all running off of you know, AC power, right? I've got power supplies plugged in. So apart from running extension cords all across my backyard, you know, all of these components could be driven by batteries, and there are relatively inexpensive, you know, solar panels that serve to kind of keep a battery charged. They're mostly used for like people who have RVs or boats or something like that. So that's something I'm contemplating, you know, just as a way to kind of detach it from the house. The Netduino has a micro SD card on it, and so as a way to kind of record configuration or log history, reading and writing from that SD card, again, is something that's supported. So that's an enhancement I might do. And then also Ethernet connection to kind of have some more over-the-wire kind of interaction with this. This is another area, you know, largely different from like a Raspberry Pi, which is running an actual operating system. If you want to have an Ethernet connection, you have to sort of write a socket to say, well, listen on this, you know, listen for a message to come in and respond to it. So, you know, one thing I will suggest is that the Netduino forums are extremely valuable. They're extremely active, and a lot of people who, you know, you can go on there and say web server for Netduino, and you'll find people who have written libraries to kind of facilitate and provide that functionality. So that's cool. One of my coworkers suggested I needed to put RFID checks on each of the chickens so that when they actually go into the coop, I could detect that, and then, you know, make sure that everybody's in before I shut the door. I thought that was a clever idea. So there's lots of other sorts of ideas. Automating the watering. I've had the idea, I think from maybe you had the mailbox detector.
That was Jamie.
That was Jamie? Okay, so, you know, I thought of like in the coop, there's little boxes where they lay their eggs. So I thought, well, an egg has some weight to it, so we could detect if there's an egg in that space, you know, and turn on a light or send a text, hey, you got a new egg in the coop. So these are all the sorts of things that, you know, could be possible based on the core capabilities of this. Two books that I'll recommend to you. These were ones that I used and found to be really good resources. So Getting Started with the Internet of Things, again, is specifically about Netduino. And he talks about sort of the interaction as you would expect with sort of an HTTP type connection to the board. And then Getting Started with Netduino, Chris Walker might have been the founder of Secret Labs. He was one of the primary guys who kind of brought Netduino to life. He himself is very active on the forums, but this is the book he wrote that talks about the particular capabilities of the board and everything like that. So I recommend those to you if you're going to do something like this. Here's all my contact info, and if anyone's got a broom, I would love some help. Thank you. Question? Yeah, we'll have questions.
Does the .NET Micro framework work with Visual Studio 2013, or do you have to have any?
Yeah, good question. So the .NET Micro framework and what version of Visual Studio? So I believe as of today they have released Visual Studio 2013 builds for that. When I first started this a couple months ago, it was only on 2010. They have done a Studio 2012, which is what I'm using currently. And then the 2013 support is maybe kind of in a beta stage, but it is coming out. So yeah, good question. Yes, sir, in the back.
How much internal memory does the Netduino
How much internal memory does the Netduino have? Let me look on my slide to see if it showed that.
Not a lot.
Yeah, it's.
Wondering if you could extend it on my SD card,
You can use that's yeah. So the micro SD card is available to sort of have capacity, but yeah, the onboard memory is pretty limited. Maybe 512 megabytes. I'd have to look. You'd have to look up on the specs. But go ahead. Yep.
So did you burn anything out?
Well, it's funny you mentioned that. So I started this whole process with a Raspberry Pi, and I'm pretty sure I burned it out because all my attempts to take a reading off any of the I/O ports just came back empty. So, so yeah, that's so for example, the one primary area where that comes into play is in regards to. See if I can send this over here. So you'll notice here how the motors are both using their own external power supplies, right? Rather than drawing power off of the Netduino. And that's probably the fastest route to burning the Netduino out is drawing too much electricity through the board itself. So that's why the servo and the motor have their own power supplies. And then as long as you kind of have a common grounding between all of those, then everything will be okay. But yeah, thankfully Raspberry Pi was $35. It still functions. I just can't read anything off the pin. So, but yeah, good question. Go ahead.
Has there been like a false positive when a dark storm comes through and knocks the chicken outside?
So the question of a false positive, like, again, what's that threshold? The thing about this is that if it detects dark and closes the door and then it lightens back up, it would say, oh, well, it's light now, so it would bring it back up. So that's the polling, ongoing kind of polling of it, where it would correct itself if there was a cloud that passed over. For a long time, I had this kind of set up in my garage, which was kind of fun because it was all plugged in and wired up, and so every time we'd go into the garage and flip the light on to put something in the recycling bin, then the door would open and the feed would, the little motor would turn, and then you'd turn around and shut the light off and it would close itself down. So that was, okay, this thing's doing what I expect it to do, even in those kind of controlled conditions as well. So yeah, we'll see when I get it actually installed in the coop, like how much further calibration I have to do to kind of get it. And that's really a lot of why I want the logging component, so I can see, like, okay, what time did it actually close the door, and does that match with me looking out the window, and is it dark enough, or did it fire off too early, or those kinds of things. So
Yeah, like there's a motion sensor trail cams and stuff with 100 views.
Yep.
Maybe put one of those out there so you can
Yeah. Yeah. So yeah, there's cameras. Another sensor that a lot of people would use are infrared detectors, like a motion detector. So yeah, you could see if there's enough motion inside the coop. Then don't close the door until you see that. Jamie.
Sorry, do you have anything to protect the chicken? The door coming down on top of it, like something that.
So not to protect the chicken per se, right? Of this falling. You do notice, so an earlier iteration of this, I've got this little latch here that is mounted kind of underside, and I had the catch so that when the door would come down, it would actually lock it in place. And the idea there was so that some eager raccoon couldn't get their hands underneath this thing, because the door itself is not real heavy. So some eager, determined raccoon could get underneath it. And so then the cord would attach to the gate latch here, so that as the motor turns, it will unhook it and then draw it up. I kind of moved away from that, at least to kind of get it running, because it actually was quite a lot of pressure to get this thing to pop forward and then pull you end up kind of pulling the whole door based on this little latch. And so I, it was, and because it was off center, I mean, there were some unique kind of engineering kind of challenges for how to do that so that it could lock itself in place, but then also easily unlock to open the door back up. So I have seen people who have built sort of gravity-based locks where they'll have triangle-shaped kind of pieces that lock onto the sides of the door and on pivots. And so then as the thing rises up, it pinches it together and we'll pull them out and then let it slide free. And so I may re-engineer that a little bit as well. But yeah, I'm a little bit in kind of wait and see mode, because if this goes out and having the door down is enough, then I'll be satisfied with that at this point. So I know it's lunchtime, so any other questions? I appreciate you guys coming out. This was fun.